Hi everyone, this is Dr. Saida Falafini from Cal Poly Pomona. In this video, I'm going to talk about absorbing Markov chains. So we want to learn what those type of Markov chains are and what type of questions we are interested to answer in this type of Markov chains. So if you remember in the previous video when we looked at different classifications of the states of a Markov chain, we said that some of the states of a Markov chain can be absorbing, meaning that when we end up in those states, we are going to stay in those states forever. And some of them are transient, meaning that there is a path that can potentially take us out of that state and never let us to get back to that state again. So absorbing Markov chains are those type of Markov chains in which we can classify the states in the Markov chain into two categories. Some of them are absorbing states and some of them are transient states. These type of Markov chains are what we call as absorbing chains. One of the examples that we talked about in the past that falls in this category is the gambling example. If you remember in that example, we said the player has $2 and at each game, the player is going to either win $1 or loses $1. If the player wins with probability of P, we are going to get to $3. If the player loses with probability of 1 minus P, we are going to get to $1. Similarly, let's assume the player has $3. If the player wins with probability of P, the player is going to have gain $4. And if the player loses with probability of 1 minus P, the player is going to have $2. We said once the player gets into $4 value, the player is going to stop and quit the game. So once the player gets to $4 value, the player is going to stay here forever. On the other hand, when the player gets to the $1, again, the player has the chance to win the next hand and again gets back to the $2 with probability of P, or loses the next hand with probability of 1 minus P and gets to $0 value. If the player also gets to the $0 value, the player is going to quit because the player cannot play anymore. So the 0 is also an absorbing state because once the player gets there, the person is going to stay there with probability of 1 in the future hands. So in this example, as you can see, state 4 and state 0 are absorbing states because once the system gets to these states, once the player gets to these states, the player is going to stay in these states for the rest of the life of the system. And states 1, 2, and 3 are transient states because we can find a path that can take us out of these states and never let us to go back to these states. For example, for state 2, this is the path that can take me out of this state and never let me to get back to these states. You can also check this characteristic for state 1 and state 2 and just confirm that state 1, 2, 3, all of them are transient states. So this Markov chain is what we call as an absorbing chain. Let's look at another example. This example is related to the accounts receivable of a firm. So this firm is selling the products and then it has some accounts related to those customers that are created. So once an account is created, is categorized as a new account. And then if by the end of the month that new account has paid the debt, it's going to be categorized as a paid account. However, if the account is not going to pay it's going to be labeled as 1 month overdue, and then one more month passes. Again, if the account is not going to pay the value, it's going to be written as 2 months overdue. And again, after 1 month, if the account has not yet paid the debt, it's going to be written as 3 months overdue. And then if the account is uncollected after 3 months, it's going to be written as a bad account. So these are all possible values for the state of these accounts that are created in this system. We can write the one-step transition probability matrix P as this matrix. So the values for our state is a new account, 1 month, 2 months, 3 months overdue, and finally a paid account or a bad debt. Okay, so I'm going to list the same states on the columns of this matrix. and whatever I put in this matrix is the values of the one-step transition probability. So here, as you can see, when we have a new account with the chance of 40% at the end of the month, this account is paid, or with the chance of 60% is not paid, so it's going to go to the 1 month overdue account. If we have a 1 month overdue account with the chance of 50% is going to be paid at the end of the month, or it's going to be not paid with the chance of 50%, in that scenario is going to go to the state of 2 months overdue. If an account is 2 months overdue, with the chance of 60% is going to be paid at the end of the month, and with the chance of 40% is going to go to the 3 months overdue. And if an account is 3 months overdue, with the chance of 70% it will be paid at the end of the month, and with the chance of 30% is going to be written as bad debt. And if an account is paid, it's just going to stay in this state forever. And if an account is written as bad debt, it's just going to stay in this state forever. As you can see here, states new account, 1 month overdue, 2 months overdue, and 3 months overdue are transient states, and states paid and bad debt are absorbing states. So since all the states that are available in this system can be categorized into 2 categories, either transient state or absorbing state, this Markov chain is an absorbing Markov chain. One important point that I want you guys to pay attention to when you are analyzing absorbing chains is that when these systems basically go through their transitions, at some point all of these states will make a transition to one of the absorbing chains, and they are going to stay there. So for this gambling example, for example, the person is going to start with $2 and is just going to continue plays. He's gaining $1, losing $1, gaining $1, losing $1. So this can go on and on and on and on, and the person potentially can make transitions between $1, $2, $3. But at some point, for sure, this person will make a transition to $4 or $0. So if $4 or $0 are absorbing chains, this person will finally, definitely, for sure, make a transition to one of these absorbing states. The same for our account receivable example. Yes, an account starts and it's a new or 1 month overdue or 2 months overdue or 3 months, but at some point after doing all the transitions, for sure this account or this system will end up in the paid state or debt state. So for sure this system at some point will end up at one of the absorbing states and it's going to stay there. That takes me to our next slide, in which I want to talk about some of the important questions that can be answered related to absorbing chains. So the first question says, if we start at the given transient state, what is the probability that we end up at any of the absorbing states? For the gambling example, what does that question mean? It says, what if we start at any of the transient state, either state 1 or 2 or 3, it doesn't matter. What is the probability that we start at any of these transient states, and then at the end we end up at one of these absorbing states? So the specific question can be, what is the probability that the person starts with $3 and at the end this person ends up at absorbing state 0, meaning losing all the money? So this is the type of question that we can ask. Or another question is that, what is the probability that a person starts at transient state $1, for example, and the person ends up at absorbing state 4? Okay, so all kind of variations that you can think of can be the type of questions that we can answer. And these are important questions to answer because when a person starts the game at one of these transient states, we want to know what is the chance that the person ends up winning or what is the chance that the person ends up losing, because for sure one of these would happen, but we want to know what is the chance that the person will win and what is the chance that the person will lose. Similarly, for the account receivable example, a person can start at any one of these transient state, but what I want to know at the end of the day is that what is the chance that finally this account ends up being paid, what is the chance that finally this account ends up being written as bad account. So for example, if an account starts as a new account, what is the probability that finally this account is paid? What is the probability that finally this account is written as bad debt? This is important for the organization because they want to know what percentage of these sales that they do, what percentage of these new accounts that they create finally end up being paid or finally end up being written as bad account, and those are basically the money that they are losing. So let's assume I'm looking at the account that is 2 months overdue. So of all those accounts that are 2 months overdue, what percentage of them end up being paid? What percentage of them end up being written as a bad debt? Okay, so these are the type of questions that we can answer for any absorbing chain. If we start at a given transient state, what is the probability that we end up at any one of the absorbing states? Okay, so that's one type of question. The other type of questions that we can answer is that if we start at a given transient state and before we reach any one of the absorbing state, how many transitions or how many time steps we expect to spend at a specific transient state before the absorption takes place. Okay, so let's again go back to these examples and let's try to explain here. So for example, it says that if we start at any transient state, let's say we start with $1, okay? How many hands or how many time steps in this problem, every time step is a hand. How many time steps or how many hands I will spend at state 3, meaning that for how many hands I will have $3 before I finally get absorbed, either get to the $4 or lose everything and get $0. Okay, so if I start, let's say, with $2, I start with the transient state $2. How many hands I will be at the transient state 3, or how many hands I will be at transient state 1 before I finally get absorbed at state 4 or at the state 0? And this is what we try to answer here, that if we start at a given transient state and before we reach any one of those absorbing states, how many transitions or how many time steps we expect to spend at another specific transient state before finally we get absorbed in one of the absorbing states. Okay, so we are going to go through a couple of examples and we try to answer these questions for those examples, and that helps you to get a better understanding of what these questions mean and how we have to calculate them. To answer these two questions, we have to rewrite the one-step transition probability matrix. In this version of the transition probability matrix, we are going to specify all the transient states, we are going to specify all the absorbing states, and when we put the one-step transition probability matrix together, we make sure to list all transient states on the top and list all the absorbing states at the bottom. And obviously, whatever order we pick for the rows, that's going to be the same order we have to put for the columns. The first couple of columns are going to show our transient states, and the last couple of columns are going to show our absorbing states. In this example, as a general case, we have assumed that we have possible values for the state of the system, and we have assumed m of those states are absorbing and the other states, s minus m, are just transient states. So that's basically what this notation means. Okay, so we have to rewrite the one-step transition probability matrix P this way. Then we are going to name that part of the matrix that is related to transitions between transient states and transient states as matrix Q. I'm going to name that part of the matrix which is related to transitions between transient states and absorbing states as R. that part of the matrix that is related to transition between absorbing states and transient states as 0, because obviously when we are at the absorbing states, we are not going to make a transition to any one of the transient states. So all these probabilities will be 0. And then this part shows the transition probabilities between absorbing states and absorbing states. And that's going to be 1, because once we get to the absorbing states, we are going to stay there. So let's see how this is going to be applied on the one-step transition probability matrix we have for the account receivable example. So in this one-step transition probability matrix P, whatever I have listed on the top are my transient state. Whatever I have listed at the bottom are absorbing states. The same here, the first columns are transient and the last couple of columns are absorbing. Whatever I have for the transition between transient and transient state, that's what I'm going to call as matrix Q. Whatever I have for transitions between transient and absorbing states is what I'm going to call as matrix R. This is the part that is equals to 0 as you saw on the notation. And this part is going to be an identity matrix I, because it's just a transition between absorbing states. So if we are at the absorbing state paid, we are going to just stay there. If we are at the absorbing state paid depth, we are going to just stay there. So that's what we have for these absorbing states. Okay, so this is basically the identity matrix I when the values of the diagonal of this matrix are 1 and the rest are 0. And also, just for the sake of notations, I'm going to call the first transient state as T1, T2, T3, T4, and the first absorbing state as A1, and the second absorbing state as A2. The only reason that I use this notation is that those are the ones that I have used in the rest of the slides, so I just want to make sure it's clear that what we are referring to. So now let's go back to our questions. Our first question was that if we start at a given transient state, what is the probability that we end up at any one of the absorbing states? Okay, so what is the answer to this question? If we start at a given transient state Ti, as an example, the probability that we will eventually be absorbed in the absorbing state Aj is the ijth element of the matrix I minus Q inverse multiplied by matrix R. And Q and R are what we are going to pick from the one-step transition probability matrix. So now let's see how I'm going to calculate. The top matrix is what I have as I minus Q. So let's see how it was calculated. Matrix Q, as we saw from 3 slides before, is a 4x4 matrix. That's matrix Q. And between all the transient states, right? So from transient states to transient states. So let me put the values of this probability matrix here. So this is the matrix Q for the account receivable example. And this is when we have the first transient state T1, T2, T3, and T4. Okay. So now I'm going to write down the identity matrix minus Q. So what is identity matrix? So obviously, if I'm going to write identity matrix I minus Q, the size of the identity matrix should be equal to the size of the matrix Q. So since matrix Q is a 4x4 matrix, I'm going to write an identity matrix of the size 4x4 so that I can do the deduction. So identity matrix is going to be 1, 0, 0, 0, 0, 1, 0, 0. Okay, so this is identity matrix I. So now, what is I minus Q? So to be able to calculate the deductions between these matrices, I need to basically relate each item to the corresponding one. So obviously the first one is going to be 1 minus 0, 1. The second one is going to be 0 minus 0.6, minus 0.6. And then 0 minus 0, 0, 0 minus 0, 0. So if I do the same calculations for the rest of the rows, so this is I minus Q, and that's exactly what you see has been written here. So that's how it has been calculated. So based on the formula, to answer question 1, I need to calculate I minus Q inverse multiplied by R. So I minus q is what we have calculated here at the bottom. We have calculated the inverse of I minus q. We went through the example on how we can use Excel to calculate the inverse of the matrices. So you can use that to calculate the inverse of I minus q. So this is what we have here. And then I need to multiply matrix I minus q inverse by R, by the matrix R. And matrix R, as you can see, is this matrix, this 4 by 2 matrix. So this matrix, I minus q inverse, should be multiplied by matrix R. And the values of matrix R are, so this is matrix R. So we need to multiply matrix I minus q inverse by matrix R. Note that here the size of the I minus q inverse matrix is a 4 by 4 matrix. The size of matrix R is a 4 by 2 matrix. So so obviously this multiplication is possible, and the size of the resulting matrix is going to be 4 by 2 as well. If we do this multiplication, the result is what we are going to see here. So this is the multiplication of I minus q inverse by R, by matrix R, and it's going to be a 4 by 2, like what we just said in previous slide. And remember, the 4 rows represents the transient state T1, T2, T3, T4. So that's what they represent here. And the 2 columns represents the absorbing state A1 and A2 that we have here in this matrix. So the 2 columns that we see here are one for absorbing state 1 and the other one are for absorbing state 2. Here, in answering this very important first questions for absorbing Markov chain, we said if we start at a given transient state, the probability that we will eventually be absorbed in the absorbing state AJ is the ijth element of the matrix I minus q inverse R. So what does that mean? It means that if we start, for example, at transient state T1, remember this is related to a new account. This is 1 month overdue, 2 months overdue, and 3 months overdue. So these are the 4 transient states we have. And the first absorbing state is the paid state, and the second absorbing state is the bad debt. If we start at any transient state, let's say if we start as a new account, the elements of this matrix is going to tell us the probability that we end up at absorbing state A1 or the probability that we end up at absorbing state A2. So if we start as a new account, so an account is in the system and it's a new account, there is 96% chance that this account is going to be paid at some point, and there is only 3% chance that this account is not going to be paid. About 4% chance that this account is not going to be paid. Let's look at this one. I'm looking at the transient state. I'm looking at the 2 months overdue account. So that's the transient state. For a 2 months overdue account, I expect that with the chance of 88%, they are going to be paid. They end up at this absorbing state, and with a chance of 12%, they are going to be written as bad debt. So they are going to end up at this absorbing state. If I have a 3 months overdue account, I'll expect that only 70% of them finally are going to be paid, and 30% of them are going to be written as bad debt. And as you can see, the numbers make sense as well, because as you can see, the probability of ending up in the paid state decreases as the accounts goes from 1 month overdue to 2 months overdue to 3 months overdue. So we can see as an account is more months overdue, the chance of the person finally pays the account is getting less and less. So we went from 96% to 94% to 88% and to 70% and so forth. Okay, that's how I'm going to use this matrix I minus Q inverse multiplied by R to answer the first type of questions that are going to be asked in an absorbing Markov chain. Okay, so that's the first type of question. I will tell you in a bit in another example on how we can answer the second type of questions in a Markov chain. The reason I don't discuss it here in this scenario is that it's not just too relevant. It's still doable, but not too relevant. So that's why I want to answer this question in an example that is more tangible, so that you get a better understanding of the question and how we can answer it. The one last thing that I want to talk about in the account receivable example before we go to the next example is this part. So this is just a general question. It's not any specific, but we can answer this type of question. So if the firm sells averages 100,000 per month, how much money per year will go uncollected? Okay, so that means they are selling. So they basically, these accounts are created in each month. So the question is that how much of this money is going to be uncollected per year. So first, this is my monthly sales. So if I want to calculate my yearly sales, I'm going to multiply 12 by $100,000. Okay, so that's going to be my yearly sales. And then from the calculations that we did here, we said that if an account is a new account, there is about 96% chance that they're going to be paid at some point, and there is about 4% chance that they are not going to be paid. So for each new account, there is about 4% chance that it's not going to be paid at all. So then out of these all money, which is my annual sale, only this portion is not going to be collected. Those are the portions that are going to be written as bad debt. So the results, which is $43,200, are the value of these sales that is not going to be connected at the end of the year. So in this example, as you saw, you're not going to tell anything about absorbing chains and transient states and absorbing states and so forth. We just explain the problem statement to the situation of this account receivable firm, and then we say that, okay, we have about 100,000 sale each month, but what percentage of this money is not going to be collected at the end of the year? So by these calculations that we do, we can find out that if these are the new accounts that have been created, what percentage of them will not be collected, what percentage of them will be connected by the end of the year.